Okay. All right. So welcome everyone. Let me see who we have today.
Sorry,
Okay.
have you live streamed yet?
Yeah, it's live stream.
Yes.
All right. Welcome everyone. I can see Christian Utsu. I can see Captain Michael. I can see iPhone. Yeah, I'm seeing some familiar names. Seeing some Vara. I will mispronounce the other one. I can see Tawakal. I can see Nina. I can see Toluwani. Akiwumi. All right, welcome everyone. Yeah, good evening. It's nice to have you guys here again. Okay, so before we jump into today's course, does anyone recall or does anyone recall what we did in our last class? Maybe a topic or maybe something you learned from the last class? Anyone? Yeah, we lost some people. Anyone remember what we talked in the last class? What we created? Okay. All right. So I wouldn't want to spend much time. Let me see. Do we have any chats? Okay. All right. So in our last class, we actually went through some regularization and optimization techniques we can actually apply in our model, right? We understood what overfitting and underfitting meant when it comes to model, and then we saw how to implement it using the Keras model. Then we also talked about other stuff that we can do to prevent overfitting, such as adding more training data and data augmentation. I think we're going to do data augmentation today. Then early stopping, whereby maybe your model is performing very well and all of a sudden the performance starts to degrade. So you apply your early stopping. Then we talked about the regularization, the reach method, the dropout method. Yeah, so that was basically what we went through in our last class. So today we are going to be treating a different topic, and it's still in line with what we have in stage C. So let me go ahead and share my screen. Um, can you all see my screen? No? Can you all see my screen?
It's still trying to share.
Can anyone see my screen?
No.
No, not yet.
Oh, that's network. My network is glitching. Is it? Can you guys see it now?
No, it's still trying to share.
Look, can you guys see it now?
Yes.
No, we can't. Okay, we can't. Apologies, guys. Your tutor is having some technical difficulties, so it's not here, but he will join us soon.
Hello, can anyone hear me? Hello, can anyone hear me?
Yes.
Can you see my screen? Hello, can anyone see my screen?
Not yet. Okay, yes.
Yes.
You can see your
That's
screen.
me. I'm so sorry about that. All right, so today I want to look at convolution neural network and how they work. Okay, so we're just going to explore how convolution neural network works, commonly known as CNN. This network are particularly powerful for image-related tasks. So by the end of today's session, you will have a solid understanding of CNN and how to implement them using the Keras framework. Okay. So here is an introduction. CNN are a typical artificial neural network designed specifically to process and analyze visual data such as images. They work by automatically detecting and learning the important features of the images, such as edges, texture, and shapes. So this capability makes them extremely effective for tasks like image classification and object detection. So you can think of CNN as having built-in eyes that can see and recognize patterns in pictures. So on the next slide is a diagram of typically how a CNN looks like. So like I said, it's designed to process and analyze visual data such as images, and they work by automatically detecting and learning the important features of images. So you can see the input down to the output, the fully connected layers, the platen layers, the softmax activation functions. So some of this stuff we are going to be seeing what they mean in the following slides. But this is just how the network looks like. So you can see that that's a horse. Hold on, give me a sec. So that's the horse, how it's detecting it, the different layers it's taking it in, the pulling. I'm going to explain that in a bit. Then down to where it starts predicting, oh, is this a horse by showing how many percentage it is. So that's what the soft marks, I think we talked about it in our last class. That's what the soft mark does. It has a way of putting our results in probabilities. Okay, I'll move on to the next slide. So we have the convolutional layers. So at the heart of a CNN is a convolutional layer. This layer applies multiple filters to an image to create feature maps. These filters are like small windows that slide over the image. The detecting features captures different aspects of the image, helping the network understand and learn important visual details. So you can imagine using a magnifying glass to examine different parts of a picture. That's similar to what a convolutional layer does, right? So you zoom in on different parts of that image, pulling layers, just like we saw when we were looking at the full. So we have the pulling layers. These layers reduce the created by the convolutional layers. That's from the previous steps. Maps created by the other layer, right? Making the network more and less likely to overfit. So the most important type of pooling is max pooling, which takes the largest the most important features while reducing the amount of computation. So you can think of it like summarizing a paragraph by picking out the most important sentence. That's just how that's how you can actually view the next we have is the fully connected layers. Several convolutional and pooling layers. We use fully connected to learn complex patterns. It's similar to how convolutional okay, so as I was trying to say, the fully connected layers, let me allow some people in. Yeah, the fully connected layers is the point where after the convolution and plane layers must have done their job, it flattens the features map into a single vector and use it to make final classification, right? So like I said, I gave an example. It's similar to how after observing the different aspects of an object with the microscope, that which was the previous layer, the pooling layer, you combine all that information to identify it. So that is the fully connected layer. Then we have the activation functions in the CNN. So activation functions introduce into our network.
Hi guys, can we hear what Goodrich is saying?
No.
Okay.
Right now, not
Apologies
at
for
all.
that. Not at all. Okay. Так, так, подожди. Нет, нет, вот так давай.
I'm so sorry about the glitches. Hope you guys can hear me now. Hello, can
Yeah,
anyone
it's
hear me
better.
now?
Yeah, it's better now.
Yeah, I'm very sorry about the whole issues and everything. All right, so we are just few more slides and we are done. Okay, so I was talking about the activation functions. I said you can consider them as decision makers, deciding whether a neuron should be activated based on the input it receives. Then we have common CNN architectures, the Linux, right? So there are several well-known CNN architectures that have been developed over the years, each with their unique characteristics. So we have the Linux, which was one of the earliest CNN and was used for digit recognition. AlexNet. AlexNet brought deep learning to the forefront by winning the ImageNet competition in 2012. We have the VGG, which is known for its simplicity and depth, using small 3x3 filters. Then we have the ResNet. ResNet introduced residual connections to solve the vanishing gradient problem in very deep network. This architecture serves as a foundational models that we can learn from and build upon. So these are just the already the available CNN architectures we have at the moment. Okay, so I think this is where we jump into the notebook. Don't know if anyone has any question before we go there. But we are going to the notebook. So if you have any question, you can please go ahead. This is going to okay. All right. We want to go through this. This is just a minor setup of a simple CNN with Keras network. So we are working with the data set we used in our last class. Why is that still not working? Just give me a sec. Okay, I will come back to that. So this is a minor setup we have for the Keras network. We can see the different layers that we are creating and the output, what it should look like.
Can you please zoom your screen?
Sorry about. Is it visible now? Is it okay now? So,
Yes, it's
Yes,
better.
it is.
all right. Okay. I'm trying to fix the other error, but all right. So these are the different layers we've brought in our libraries what we require to plot. We load our data sets. Right. This is the same data set we used in our last class. Okay. Then we process the data reducing the size to fit in. Then we define our model here. We're using a sequential model with different filters and the dense layer, the activation function in each of them. The max pooling, we talked about pooling some minutes ago. It picks out the most important features after it must have passed the convolutional layers. Then we compile it, we use the Adam optimizer, and we are tracking the accuracy. So I've run this, it's just going to download the data and then compile this model. Okay, so here is where we train the model. Already in our last class, we talked about this epochs and yeah, how it's also part of the optimization. So you sometimes may increase it and you see an increase in the accuracy of your model. And sometimes you may reduce it and it even performs more better than when it has many number of epochs. So this is where we train the model with our available data sets and our validation function. So we can see that the accuracy is increasing over time, but the validation is actually reducing. Yeah, it's increasing on this end. Okay. So yeah, today is just basically how to create this stuff, the different layers, convolutional layer, the pooling, the fully connected layers, and then your output. Right. So it's just similar to what we've been doing. And I think the part that will be different is the data augmentation part. Okay. So this is the graph of what the accuracy looks like, our main accuracy and the validation accuracy. So this is what it looks like. And yeah, we can see the model is performing relatively good. And who knows, maybe if we increase the number of epochs, it's likely going to be increasing to maybe 0.8 something. Yeah, I think I just repeated this stuff. This was when I run that same code and I'm having a different output. But yeah, they're just still within that 0.6 to 0.8 range. Okay, this is actually where I was having a local set. Yeah, so here's where we do the prediction. I'm actually running it now. So may take time. Okay, so we can see the predictions. Um, this is not expected. All right, so we can see its prediction on the data sets, and just below it is the percentage, like how accurate it's predicting it. It's classifying this as a cat with a 527%. This blue line is actually the predicted, no, the true level and the predicted level. Then this predicted this to be a ship with this percentage of accuracy. Yeah, 780, frog 664, airplane. So just below the visuals are the percentage, how accurate it's predicting those images, and the level it's predicting it. Let's see if we're going to get anyone that's wrong. So far we have it's predicting it accurate. Okay, here, look at this. So it's classifying a dog as a bird. So there is one misclassification that happened. Classifying a dog as a bird. So we have one misclassification here. Uh, so yeah, this is the predicted labels and the true labels. Yeah, here it classified a sheep as an airplane. So this is also wrong. That is why it's highlighted in red. Is data augmentation. So we talked about data augmentation. Is actually saying the images to better to train the model maybe in a complex way to if it is this way, will it still be able to recognize? Or maybe if you turn a cat upside down, will your model still be able to recognize it as a cat? So that's what data augmentation does. So it's a technique to increase the diversity of your training data set without collecting new data. It involves applying random transformations such as rotations, translations, and flips to the images, helping the model generalize better. So in Keras, we are using the image data generator for that. I don't think I've run this. But let me just copy this and run it again. So rotation, we are rotating images by 40 degrees. Okay, I've run this one now. We're rotating the images, like 40 images by 40 degree, right? Then this width shift range randomly shifts the images. What's up? This that's left to right by 20%. Then the height shifts it up, like vertically up and down by 20%. Then we have the clear range, applying random shade transformation, then zooming inside the pictures by 20%. Then horizontal flip. So we are randomly flipping the images horizontally. Then the fill mode nearest strategy used for filling in newly created pixels after a transformation. So nearest means newly created pixels. We take on the value of the nearest pixel. Then after doing all these different adjustments and the rest, we use it to train. We use it to train on we use it we use it to train on our images, and then we just visualize the example of augmented images we have. Then you tell it. Okay, it's the same thing. So here's what we have. This car, I think this car was flipped, if I'm not mistaken. This was rotated. But you can see the adjustment it has made to some of these images, though it's not clear. It's not that clear. So yeah, this is how you can actually apply data augmentation to it, and it will just help train your model better. I think I'm seeing some chats. Will- Hold on, I think I have some questions here. I think it's one after the other. Okay, so I'm saying, where is there a tree in the input shape? Is there any question before that? Okay, so the tree, let me scroll down to the place. I'm coming now. Oh, I guess you're referring to this. Is it this one? Yes. I guess you're referring to this tree in the layers. Please, can you confirm that you're referring to the tree in the layers? I'm not sure there's a way to make the images clearer. That's just how I actually tried, but yeah, it wasn't getting any clearer. The person that asked the question about the tree in the input shape, I'm not sure which place you're referring to. Are you referring to this? I'm not sure there's any other place that okay, I'll take it that you're referring to the model. Okay, yeah, okay. All right, so let's break it down. The tree in the input shape, that's the 32 tree, corresponds to the number of color channels in the input images. So the 32, these are the height and width of the images in pixels. So that cipher, let me scroll up. This cipher then data set, that is how the image, like the shapes of the images is. That is the structure it has. So the 32 are the height and width of the images in pixels. Then the tree is the number of color channel, according to the research I saw online. See if I knew someone was going to ask. Represent the color channels in the images. So in this case, images are in RGB color format, so which corresponds to the tree values red, green, and blue channel. So that 32 tree specifies the inputs to the model. Sorry, specifies that the input to the model will be images that are 32 pixels wide, 32 pixels tall, and have three color channels. I don't know if that's clearer now. I'll go on to the next question. Is I'll take your one after the other. Okay, the next one here says, does the layout of the dense, does the layout of the dense layer and flat layer matters? Can I just add in whatever? Just add in, can I just add it? You're confusing me with the way you're writing this stuff. Can I just add it in whichever order? So I think it matters. You don't just add it in any order. Sorry. No, you don't just add it in any order because there's a difference between flatten and dense, and I think I explained that in our very first class. So the other layer in that neural network is very, very important, particularly that dense and flattened layers. It's very, very important and cannot be changed just like that, right? So each type of layer has a specific role and must be placed in the correct sequence for the network function properly. So yeah, flattened layer. Okay, I think I'll just have to explain. It used to convert multi-dimensional by the convolutional layers. So you flatten that output that comes out from the convolutional layers, the one we saw in that picture, which is likely this first layer, pulling. So whatever is coming out from here is flattening it from a 2D to a 1D vector. That's what it's doing. It's flattening it from a 2D to a 1D vector. So then the dense layer is used to perform the final classification. So dense layer takes in a 1D vector. Right? What is coming out from that convolutional environment, that one I just highlighted, it's in a 2D format. So what your flatten layer does is to flatten it into a 1D vector that can now then be fed into that dense layer. And we have two dense layer here. So once whatever is coming in here, this guy is going to flatten it from a 2D layer to a 1D layer that this guy accepts. I want to believe. So the other matters. The other matters. You don't just put it anyhow. Uh, there may not be time to teach how to use generators. Excuse me. There may not be time to do this. I'm going to skip that. Is there a way to make the image clearer? I'm not sure there is. What happens if it is a gray scale? Well, okay, that is an interesting question. What happens if it is a gray scale? So I think this is where your color comes into play. So if the images are actually in grayscale, from my understanding, the input shape would change to reflect the only one color channel listed of the tree. So when you say grayscale, you know that it's just black and white. So grayscale images have pixels that ranges from 0 to 255. That is black to white, and each pixel is represented by such. So you have to adjust that input layer. I don't know if you understand. You will need to adjust this input. You guys will not finish with the question. Hello, can you guys hear me?
Yes, we can.
Okay, I thought I lost my connection again. Okay, so I was saying we will need to change. Sorry, the grayscale. If it is a grayscale, we'll need to adjust the whole color of everything to one, because the color that is now it's now taken in is not it's not green anymore. It's no more red, green, blue. So at that point, this input shape you have here, you will change this three to one like this. So remember I explained this is the height, the width, and then the color scale. It was three initially representing the red, green, and what is the other one? RGB, red, green, blue. yeah. So if it is just a gray scale which is black and white, so yeah, it's just going to be one. So here is the only place you need to adapt it that in, and probably from I don't think there's any other modification you do. So that's where you adjust to fit in. So what does the shape looks like? Assume it's a 32 by 32 pixels. I'm not sure I understand the context of your question, or you may want to rephrase it. Is there a reason why the convolutional layer changed from 64 to 32? Yeah, that's the filters. Okay. I think it's just going to be helpful. I guess, no. Look, can anyone hear me?
Yes, we can hear you.
Okay. So my network is lagging a bit. This first question, I'm not sure I understand this first question. Now, is there a reason why the convolution changed from 64 to 32 in the second layer? Yeah, that should be self-explanatory with the image you saw earlier on. The size of the hold on, let me put that question from 64 to 32. Yeah, the size of the layers keeps on reducing if you notice from the image. So the first pooling layers, let me just pull up to here's what I'm trying to say. Think, we are saying that these sizes are reducing, right? So it's just likewise how actually increasing. Sorry. So the first pooling layer you saw there is taking in the 32 filters, right? With the padding size that's 32. Then the second one is actually 64. So you're not asking why it changed from 32 to 64. But I would say it's because of the different layers we have. Okay. So the input shape of the image is 32 by 32, and that's when it passed through the convolutional layer. And you can also increase it to 64 at the next step, putting the padding size the same as the previous one. So it's just going to reduce the other size. Just like, look, can anyone hear me?
Yes.
Just give me a second. Who's put this there? Who's putting it? Sorry, I'm coming over about something. Ouch. Sorry about that. That's attend to something. Okay. Yeah. So I have a question to answer. 3234. Yeah, that's correct. So yeah, you're referring to the numbers of filters in the convolutional layers. They actually vary depending on the architecture you're using, like I was trying to explain. Okay. So typically the number of filters usually increase in any deep layer network, and it's as a it actually as a result of deeper layers captures more complex and abstract features, right? So it's just a pattern we have in deep layers to increase the filters to capture. That first stage is just 32. We may not really pick out a lot of things, right? So we increase the filter in the next level to, I'll put it this way, to capture more complex pattern out of the images that is being passed in. So that's just how I can explain it, right? So you increase the filter to capture more features. Yeah. So there could be other reasons attached to it. Yeah, you can add multiple can you add multiple metrics while compiling the model? It's already in the list. It's already in the list. So you can add multiple metrics to capture whichever one you have. So far we've been working with the accuracy. So you can put in other ones. All you need to do is like I said, it's already in the list. Where is it? It's already in the list here. So you can capture the accuracy, like we have the ones that we've seen so far. Let's say precision, for instance, and then you can add recall too. Yeah, you can add them like this, and you can be tracking each of them. So it's just going to be giving you the results you want. Uh, why is it trying an error? I think I'll have to restart this. Sorry? Oh, no. Okay, we don't have time to fix this, but here is how you can actually add in. Here's where you can actually add in more metrics to track, but you need to adjust because what this was created was just for accuracy. So maybe that's why it's throwing an error. So you just need to readjust this side to capture what you want to do. But yeah, you can add as many metrics as you want. All right, so we're already out of time. I've not seen any other question. You haven't answered the dense layer question. I did. I did. It was where I explained that dense layer takes in a 1D vector input. So the one that is coming out from the convolutional layer is actually in a 2D format. What is coming out from here after the whole max pooling and everything, it's in a 2D format. So this guy flattens it to a 1D vector input, which is what a dense layer takes in as an input. So yes, the order of arrangement matters in your neural network. So you don't just put it anyhow. The order matters. It's very important. So I don't know if that answered your question. All right. in preparing to digital. Try to understand what you're saying. Okay. Yeah, the 64 is actually the fully connected layer. Hold on, let me show you using the image. The 64 is actually representing the fully connected layers, like we saw in the images. Sorry, in the picture in our slide. This is what it looks like. That's then let me use the other one. Yeah, I'll share the link. I think it's already late. See this place. That dense pen is actually here. Well, I say it's this one. I'm giving a scenario. I'm not trying to say that is the same thing here. Giving a scenario. So that 64 is likely a place like this, and the images we are trying to classify, they are just 10. They are just 10 of them. We have just 10 images. So that's the last layer we are seeing. We have just 10 images in our data set. So that 64 is representing the fully connected layers. Then that's then 10 is the output layer for the 10 classes we have. We're already out of time. Let me just quickly show the notebook link. Give me a sec. It's loading. Okay. That's in the link. So check the income message and pick up the link. Then we'll end the meeting in the next 2 minutes. This is time. So I've dropped the link to the notebook. Mind you, I made some adjustments to that notebook, so I'll likely fix it before you start making use of it. All right, so I've dropped the I just dropped the link. You say you can't see it. I've dropped. Okay, sorry. Sorry. I was sending it. Okay, I sent it now. I didn't know I was sending it to someone privately. All right. I'll see you. It's saying we need access. Sorry, sorry, sorry about that. Let me go to it's office. Okay, yeah, I've resolved that. I've sent in another link. Please confirm that it's open before I end this meeting. All right. Thanks guys for turning off. I'll see you guys in the last class. That should be on Monday, if I'm not mistaken. But yeah, I'll see you guys in the next class. And thanks for turning up. And bye.